Hey everybody, we are here to discuss our first type of spectroscopy. This is called infrared spectroscopy, also known as, come on, IR spectroscopy. Alright, one thing that you'll notice as you progress in this class, and also other chemistry classes if you take them, chemists use a lot of instruments to figure out information about their samples. This could be a number of different things. It could be the concentration of a given sample in a particular medium. It could be the identity of a sample. It could be monitoring the progress of a chemical reaction. Lots of different things that chemical instrumentation is used for. IR spectroscopy is going to be one of the most important pieces of instrumentation or that we use to figure out information about an organic sample. All right. Why do we use IR spectroscopy? We use it for a very specific reason. We use it to identify functional groups that might be present in a given molecule. We're going to see, like I said, multiple types of spectroscopy throughout the course of the year. They all have different purposes. IR is specifically used to identify functional groups, to identify chemical families that the particular sample might belong to, right? It's not so great if you're trying to figure out the exact structure of something, but as you'll see later on in the year, a lot of times what we can do is we can use IR in conjunction with another spectroscopy to sort of get different pieces of the puzzle to fit together into an overall picture. All right, so to begin with, IR spectroscopy is a type of what we call absorbance spectroscopy. And you guys probably have done something kind of similar to this, maybe in a previous chemistry class or maybe a biology class. If you've ever used something called a visible spectrometer, that's where you had a cuvette, a square cuvette, and you may have programmed in a certain wavelength of visible light and measured the absorbance. I know we did this in a Gen Chem lab experiment last spring. Right, that's a type of absorbance spectroscopy. This is very similar to that. One big difference is that we don't use, hold on, getting something up here. We don't use visible light. We use infrared. All right, so just to refresh you on what infrared radiation is, this is our old friend, the electromagnetic spectrum. And you can see, as you've probably seen in numerous physics, chemistry, and or physical science classes throughout the years, that different types of radiation exist as waves with different properties, such as differing wavelength, differing frequencies, differing energies, right? So we have the traditional kind of spectrum here. On the left side, we have the very, very high energy, low wavelength waves, the gamma rays. These are the ones that really cause damage whenever you get radiation sickness. They're also what were used to turn Bruce Banner into the Incredible Hulk, in case you were wondering. All the way to the other end where we have radio waves, very, very, very long wavelengths, generally very, very low energy, considered harmless. All right. In the middle, we have something called visible light. These are the lights. These are the waves of light that we can actually see. And of course, you can see the different colors of the rainbow here. Roy G. Biv. Excuse me. Roy G. Biv. Our human eyes can discern the individual wavelengths within this range to see different colors. Just to the right of that, we have infrared. Now, infrared is all around us at any given point. We can't see it, right, because our eyes just are not attuned to that wavelength. But it's there. You see it used a lot in like thermal cameras. The weather reports use infrared cameras quite a bit. We use infrared in this type of spectroscopy. So we're using light specifically within that range. All right. Come on, whiteboard, reload. Dude, come on. Whiteboard is slow sometimes, so let's give it a minute. By the way, I don't have coronavirus. I just have allergy sniffles, so if you hear my voice sounding a little funny, that's why. Don't be freaked out. Okay, here we go. All right, so in a nutshell, if you look at a schematic of like all the different pieces and parts and stuff of an IR spectrometer, it's very, very complex. Here is the nutshell version for you. This is basically the net effect. So basically at the beginning, you have something that serves as a source of infrared radiation, an IR lamp, basically. And what this does, this shoots out IR radiation, and you see I'm drawing a whole bunch of arrows here. This is to signify that it's actually doing it within a range of different frequencies. So it's not just one wavelength or one frequency of IR, it's doing a full scan throughout the entire IR range. All right? And this is being shot at our sample. All right? And the sample can do one of two things with that IR radiation. It can either absorb it or it can transmit it. All right? So, let's say over here we have the I'm never going to be able to get all this into that box. So, we have the detector. All right, so you have something at the end that can detect the presence of transmitted IR. So some of these frequencies will get through, right? And they'll be detected by the detector. However, not all of them will, because some of them will be actively absorbed by the sample. All right? The waves that are transmitted to the detector, these are picked up and then translated to squiggles on a page, which you guys are going to learn how to interpret. All right? One interesting question is why? Why does one particular frequency of IR get absorbed in a sample and another frequency gets transmitted? It all has to do with movement and motion within molecules. All right? I've mentioned molecules before. They're not just static. They're not just sitting there perfectly still waiting for something to happen. They're actively moving, right? You know they bounce back and forth within space. We've talked about rotation, right, around single bonds. There's a couple of other types of movement as well. All right, and these can be classified as vibrations or as vibrational movement. And there's two different types, two different broad types that IR can pick up. They can pick up stretching, and they can pick up bending. So you can literally think of a bond in a molecule much like, an arm or a leg or a spring, right? Let's just say we had water. This is where doing the virtual learning, it takes a little bit away because I have this awesome way in class of getting people to participate. I get a volunteer and I trick them into actually demonstrating these vibrations. It's all in good fun, but it does liven things up a little bit. Unfortunately, I don't have that option here, so I'll try to explain it the best I can. All right? So let's just say, we're talking about the movement around this bond, the bond between oxygen and hydrogen. Again, think of that bond between oxygen and hydrogen much like a spring. It can stretch back and forth, right? And it constantly does. Same thing with this one, right? That one's constantly stretching back and forth. If we look over here, here are some computer animations. Here's a couple of different types of stretches that you see. Sometimes you have these two stretches, these springs sort of bouncing back and forth in pattern with each other, right? The one on the left that says symmetric stretching, you see they're going back and forth, back, forth, back, forth with each other, right? It almost looks like you're rowing a boat. That's a symmetric stretch. Then you have the, they call it anti-symmetric here on the Wikipedia page. It's also called asymmetric, whatever you want to call it. Either one of those is fine. But you see here, they're still doing the same thing, but they're doing it out of sequence with each other. One's coming in, one's coming out, one's coming in, one's coming out simultaneously. I always like to use the analogy that, if you're pretending to be a water molecule, so you stand there, your fists are like the atoms, your arms are like the electrons. I love to say for the asymmetric stretch, just to pretend there are two people that you can't stand on either side of you, and you're alternating punching them in the face. Boom, 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 boom. That really seems to speak to a lot of people, which is both kind of cool and kind of scary. All right. One thing you'll notice about the stretching vibrations here, whether they're symmetric or asymmetric, is that they do so in a rhythm, a pattern, a certain frequency, if you will, right? They're not just randomly, doing it pretty fast and then going slow and then stopping and then starting again or anything like that. They're constantly going in a particular rhythm, a particular frequency, right? This is what causes absorptions within an IR spectrum. So let me write this. Absorptions occur when the frequency of IR radiation is the same as the frequency of a vibration. Okay? So if you happen upon a particular group that vibrates on a certain frequency, and that IR wave has the same frequency, it'll get absorbed. If not, it'll get transmitted. All right. There's other types of vibrations as well. Whoops. Where did it go? There we go. There's other types of vibrations as well besides stretching. They're called bends. And there's actually lots of different types of bends. Here's just a few of them. With bends, you can see here, the bends, the bonds aren't stretching here, but they're basically kind of moving side to side or back and forth into or out of a plane. All right, and so you have several of them here that are mentioned. Scissoring, it's kind of like the same type of motion you're using when you do jumping jacks. Rocking back and forth. Let's say you're at a concert and they play a power ballad or something. I may be dating myself there. Wagging like a dog's tail, twisting. And there's actually a few others as well, but this is a good general representation. Again, you see all of these movements have a particular frequency, and again, if a frequency of this matches up to the frequency of IR, you get an absorption. There are important representatives of each one of these. Probably for your sake, at this point, you're going to be most interested in the stretches. We're going to look at far and away more at stretches with just a couple of important bends here and there. All right. All right. So now that we know why we get absorptions, we said the whole point of this was to take a look at some squiggles on a page to give us some information about a particular functional group or groups that might be present. So we should probably take a look at a spectrum. Let me sketch out a sample spectrum here, and then I'll show you the real deals. All right, it's basically just an XY plot. All right, on the x-axis you have frequency of radiation. However, we have a special term for this when it's applied to IR. It's called wave number. All right, wave number is just basically a special name for frequency. We measure it in units of inverse centimeters. All right, and on the y-axis you can have different things. Most often it's plotted as percent transmittance, and that goes from 0 to 100, as any good percentage system would. Wave number looks a little odd, probably to you. It actually decreases as you go left from right. And you can program in different wave number ranges. For the most common spectra, you usually go from about 4,000 to 400 inverse centimeters or so. This is all within the IR range, and so what the machine will do as it runs a spectrum is it will scan progressively from one end of the IR range to another, the 4,000 to the 400. All right. So most of the time, most of your light is being transmitted. All right. So it'll start the scan at a frequency of 4,000. It'll kind of be close to 100. And then all of a sudden, you'll reach a particular frequency that matches up to the movement, the vibration of a particular group in your molecule. And then all of a sudden, you'll get an absorption. What happens to your percent transmittance when your absorption goes up? Percent transmittance goes down. So you might see it start to do something like this. You go along, you get out of that range, you have high transmittance, you hit a different frequency that can be absorbed, and so forth. And you can see there are our squiggles on a page. Okay? Alright, so there's different parts of this spectrum that we can divide it up into. There's two big pieces. All right. Let's make, and the dividing line is at about 1,500 inverse centimeters. All right. So we're going to sort of draw an imaginary line right over there. Anything that's greater, that's 1,500 or greater, is referred to as the functional group region. All right, greater than 1,500 is the functional group region. Anything less than 1,500 is called the fingerprint region. All right, one of these regions is much, much, much more reliable than the other one. And that's going to be the functional group region. That's where you're going to do most of your analysis. Reason being, within the functional group region, it doesn't matter within a family which exact molecule you have. For example, let's say we had alcohols, right? And there's lots of different alcohols. We could have methanol, we could have ethanol, we could have 1-propanol, 2-propanol, 1-butanol, 2-butanol, pentanol, etc., etc., etc. Tons of different alcohols. No matter which alcohol you have, you will get a reliable signal at a particular spot in this region, right? So you have a representative peak or two that says, hey, I'm an alcohol, all right? The fingerprint region is a little different because, and you can kind of infer this from the name fingerprint, fingerprints are meant to be unique, right? Unique individual identifying characteristics. You could have 10 different alcohols that you run a spectrum of. They might look very, very similar in the functional group region, but they're all probably going to look different from each other in the fingerprint region because each one of them sort of has their own unique stamp that they put below 1,500. And that makes them very, very difficult to identify as a family, with a couple of exceptions. There's going to be a couple of signals that we will look at in the fingerprint region, but only under certain circumstances. Most of the time, the fingerprint region is not considered very reliable. All right, so you're going to be doing most of your analysis in that functional group region. All right, let me erase this. Okay, let me show you the real deal. Whoops. This is a really good site. It's a tutorial hosted by the University of Colorado at Boulder, and I'm going to be using it quite a bit and showing you some different things. We have a bunch of different functional groups over here on the left side. I'm going to just click on one let's say I'll just click on alkanes. All right. Okay, and you can see here is a typical IR spectrum. We have percent transmittance on the y-axis, wave number on the x-axis. You see high transmittance until we get to low portions or low percent transmittance when we get absorptions. All right. If you look at this, we've already talked about the fact that you can help identify things by their wave number range. Right? There's a couple of other features as well. We can look at both the size and the shape of the peaks as well. So, let's make a list. 3 things to analyze. Number 1, of course, wave number. Certain functional groups, certain types of bonds, like OH bonds, C double bond C, NH, different types of bonds will have certain characteristic ranges in which they appear. In fact, if you go back to this tutorial, you'll see at the bottom of the left frame, references, you'll see list of characteristic IR absorptions. This is also referred to as a correlations table. All right, and you can see it's got it nicely organized here. Over here on the left, we have wave number. So we see that, between 3640 to 3610, we have OH stretches of one type. Then we have another type of OH stretch between 3500 3200. We have NH stretches that commonly appear between 3400 and 3250, etc., etc. And then it tells you what type of functional group that those types of stretches indicate might be present. Right? Whenever you're doing or you're trying to analyze an IR, I would definitely recommend having one of these correlations tables present. This one is very, very good, but you can find them pretty much anywhere. Your books, your textbooks will have them. You can Google them and find all sorts of IR charts online. So it's never really that hard to find one. All right. So that's one thing. We can also look at the intensity. That's basically how big the peak is. How strongly does it absorb? Right? And we have 3 categories. We have strong, moderate, to weak. Right? So if we look over here at our sample spectrum, right? I can't, the stylus doesn't show up here, but I'm pointing at where it says 2971 and it says CH stretch. You see how that peak had a very, very large absorbance? The percent transmittance went all the way down to like 10% or so. This would be an example of a strong peak, right? Lots of absorbance, very large in appearance. Or if you go over to the other side, then let's just go into the fingerprint region. You look at that peak at 1383 that says CH methyl rock under it. This peak showed some absorbance, but not very much, right? It didn't absorb very strongly. This would be a weak peak, right? I would say the one at 1470 next to it, CH scissoring, this would be more of an example of a moderate peak. And unfortunately, and this is common, different sources, like different correlations tables and other sources, will sort of define these a little bit differently from source to source. If you have one that's sort of on the borderline, one source might call it strong and the other one might call it moderate. And then there are other sources that have conglomerations. So you might have moderate strong or moderate weak, right? Here's a good general guideline that I use. I consider a peak a strong peak if it's in the lower third of your percent transmittance scale. Right? So you see here, whoops, come on. The peak at 2971 is firmly entrenched in the lower part of that y-axis. So I would classify that as strong. Moderate would be in the middle third. Weak would be in the upper third. All right? And then the last thing that we look at is the shape of the peak. They can appear in different shapes. Again, we have three categories. We have sharp, moderate, and broad. And that's basically how pointy the peak is. Again, going back to this one, peak at 2971, very, very pointy, almost like a steak, very needle-like. That would be a sharp peak. Same thing for the one at 2863. You can have some that have much more rounded edges and are more spread out. For example, classic example, in alcohols, you see this peak at 3391. That's an OH stretch. You see how it's very, very rounded and it's very, very widened out? That would be a good example of a broad peak. And a moderate one would be, somewhere in between. So if we look at amines, for example, look at the NH stretches here. You see how the peaks at 3442 and 3360, they sort of have a point at the end, but definitely not nearly as sharp as the other ones. It's broadened out a little bit, but not nearly as much as the OH stretch, right? This would be in between. This would be a good example of a moderate peak. And you'll see these things referenced in your correlations table quite a bit. You see little letters that appear. Like for this first one, you see parentheses S, comma, SH. That stands for strong, S for strong, and SH for sharp, right? So your correlations table might include not only a description of the wave number, but also a description of the peak size and intensity. All right. I am going to cut this one off right now because my wife's about to give me a call and try to arrange a meeting to swap keys for our cars. So I don't want to be in the middle of something. I will pick up with from this point with another video shortly. All right, until then, see you later.